Morty, we've got to turn the project in early.
Hey, how's everyone doing? It is a warm day, and I went out, did my presentation, went really well, I think, and shout out some UT students were there. I was like, what? They're like, oh, we done our Clifton Strengths. And I was like, yeah, we did that at UT. And they're like, we go to UT. And I was like, that's awesome. I'm treating myself today to a Red Bull. I guess it's a translucent bowl, but... So you can't see me through it. You see the background. It doesn't know what's behind me. Okay. We'll get serious here in a second. We'll load up some chapter 16. If you're in the chat, feel free to jump in. Maybe you get bonus for being here, saying hey. And let's do this. Ooh, came back, relaxed for a moment, got some lunch. Had some lunch there too. Just needed more lunch. Got my sandwich. Gotta eat that healthy food. Wasn't that healthy there, but... Hey, Jaden, good to see you there. Let's throw you some 5,000 points. We're gonna start some chapter 16. And... be able to complete the full thing. We'll do the homework to start, then we'll do a little bit of the quiz. If you have a quiz question, let us know. But it is so warm today. It's getting too warm. I like winter. You can escape the cold. If it gets really cold, you can put on like 10 jackets. I mean, I don't know, if it's absolute zero, you're kind of done for, but I like the cold because you can always escape the cold. If it's too hot, and you gotta be like, it's too hot. You can't escape it. Okay, let's start up the homework over here. Here we go. Okay, we got the first question on the screen. And we're going to mark it in the notes. So if you're here, you get to follow along and do some of this work with us. Now, I know I solve a lot of these, and that's kind of the cool part, but I want you to be able to know some of these answers and know how to solve them. So let's take a look. We are at the first question at the 3:16 mark. Stat Tool 1, Chapter 16 homework. Question 1. So the first thing is talking about here is p-values. The p-value is the probability of our results or results more extreme happening by random chance variation given that the null is true. And what do we mean by that? What's the point of that? Well, it's like to say, I can run a mile in 6 minutes. So if I make that claim, then you would expect me to run a mile in 6 minutes. But if you were to see me run a mile in like 8 minutes, that is what you observe. And we're not actually solving the math here. We're just pointing out what a p-value means. You would say me running 8 minutes or slower is unlikely by random chance given I'm a 6-minute mile runner. The most likely thing for me to do is if you observe me run something very close to it, like let's pretend here a 6:02. And that would be very likely, or something more extreme than that. So, hey, Brando, good to see you there. So the p-value tells us how likely what we saw is given the null is true. Oh, I meant a different color right there. So someone running 6:02 is a more likely result, given someone is a 6-minute mile runner, than somebody running like 8 minutes. And so what does this mean? Well, the p-value lets us know how probable the null is. So a p-value of 0.01 means that the null is false. Well, it'd be good evidence against the null. So whether or not the p-value provides enough evidence against the null depends on your alpha value. The alpha value is just the bar at which you say you have enough evidence. And when the p-value is less than alpha, we say we have enough evidence. So you should know what alpha is. So if we're going to reject the null, then we need to have a p-value less than alpha. So it really would depend. Well, this one right here, though, the way they're phrasing this p-value provides evidence against the null, but it does not show it's false. That's better. And you could reject the null if the p-value is below alpha. We don't show the null as false, though. So I'm actually going to go with this one. Because we don't show the null as false, we just have reason to believe it's false. We reject the null because we have evidence for an alternative. I believe it's going to be this one. I got scared. I was like, wait a minute. A p-value of 0.01 means that the null hypothesis has a 0.01 chance of being true. No. A p-value of 0.01 means what we observed has a 1% chance of being true given the null is true. I might have said one too many truths. Someone running in, let's say, a 6:30 mile or slower would only occur about 1% of the time given they are a 6-minute mile runner. We're just making this up, but just showing it visually. So this probability right here, this 1%, would be someone who runs 6-minute miles. If you ask them to run a mile, only 1% of the time would they run 6:30 or slower. Doesn't mean that the null has a 1% chance of being true, it means what you observe would occur about 1% of the time given the null is true. The p-value does not provide the probability that the null is true. It's the probability of what we saw given the null is true. So it's moreover the probability of what you see given the null is true. A p-value is evidence against the null. Yeah, it's kind of... Yeah, I do agree with this. That's probably going to be true. When we do evidence for the alternative, but that would be evidence against the null to reject the null. So you get evidence to reject the null. You don't need evidence to stay with the null. So a low p-value would be evidence against the null. We'll just read these other ones. The p-value provides evidence for the null. No, you believe the null unless you have evidence against it. Whether a p-value provides evidence for the null depends on the alpha level. I'm iffy on that one right there. Sufficient evidence, it should say. This p-value proves... We don't prove the null. So 1 and 4 are wrong. It's either 2 or 3. Whether a p-value provides evidence for the null... Wait, evidence for the null. No. Shouldn't say evidence for the null. It should say evidence to reject the null. Yeah. Just the way this is phrased, it could have been iffy, right? If it says whether a p-value provides evidence to reject the null, we don't get evidence for the null. You get evidence to reject the null. You have evidence for the alternative. So a p-value that's very low would be sufficient evidence to reject the null. So the p-value of 0.01 means we should definitely reject the null. Depends on alpha. When you reject the null, 100% depends on your alpha level. If you use an alpha of this and you get a p-value of 0.01, you would not reject the null. When the p-value is low, reject the null. When the p-value is high, just let it fly. If that's your alpha level on the right, you would not reject the null here. So whether we have enough evidence depends on the alpha level. So you can't always say that that's enough evidence. You got to do the alpha level. So good stuff right there. We got those all correct. You should know the theory. You should know what alpha is. You should know what p-values are. It's very important to know the theory on this. Theory helps. It went great, Emily. It went really good. There were some UT students there. Shout out UT students. And it went really well. I was worried I wouldn't do enough time. And I looked at my watch and I was like, I've got like 12 minutes. So I finished up and I went to questions. I think I finished with like 4 minutes to spare. And I was like, come on, one more question. No one was doing anything. I was going to press the issue. But went really well. And funnily enough, it was like very close to my house. Not very close. It was near the Publix we go to. But it was just funny to me that like, I was just like, well, I just kind of went home. And then I drove back. So I drove all the way home. And I drove all the way back. But it went really well. So thank you, Emily, right there. 5,000 points. I'm very happy with how it went. I've been drinking a little Red Bull, a little translucent. This is fake white Red Bull. Thank you, Emily. And yeah, I think it went well. They seemed very receptive. Got a plus. There was like 70. There was like about 8 tables, 5 people per table. There's probably 40 to 70 people there. Like rough estimate, maybe 50 plus or minus 10. I am 95% confident the true amount of people at that conference is contained in the interval 40 to 60. Okay, enough confidence intervals for now. Maybe I'm only 80% confident because that was a very on-the-fly calculation. I am 80% confident the true amount of people at the conference is contained in the interval. But that was still a lot. Like there was a lot of people, a lot of professional people, a lot of people very dressed up. I wore my dress-up clothes too. Next question. It is better to use an alpha of 0.05 than an alpha of 0.01. That's just researcher preference. You pick your alpha level. It will interchange your type 1, type 2 error. Increasing alpha increases type 1 error. We did this today. Made a really good graphic right here where we talked about if you increase alpha, you will increase your type 1 error, but you decrease your type 2 error, but you increase your power. So it's a trade-off. If you decrease alpha, you increase your type 2. If you increase alpha, you decrease your type 2. So they're inversely related. They're not complements. So it really depends on what type 1, type 2 errors you want. Usually everybody just uses 0.05. So Rock knows.
It doesn't matter.
It doesn't really matter. I mean, just use 0.05 unless otherwise stated by problems or research or anything like that. If we use an alpha of 0.01, then a p-value of 0.001 is statistically significant. True or false? What do people say? If we use an alpha level of 0.01, that's the bar, and we get a p-value of 0.001, is that statistically significant? So an alpha is the bar by which we have to go under to find statistical significance. So with an alpha of 0.01, is 0.001 p-value statistically significant? So it's saying we use an alpha of 0.001. So this is your alpha over here. and then we get a p-value of 0.001. So statistically significant just means p-value less than alpha. And yeah, that's statistically significant. That's all you have to do. That is true as true can be. Don't even read the other answers. It's just like, well, yeah, it's p-value less than alpha, statistical significance. It was, if we use an alpha of 0.01, then we reject the null if the p-value is this. When the p-value is low, reject the null. When the p-value is high, just let it fly. As in, don't reject the null. So that's true as true can be too. If the p-value is 0.01, we reject the null for hypothesis for any alpha level greater than 0.01. Such a weird way of phrasing it. It's saying if you have a p-value of 0.01 and then you set alpha higher than this, you would reject this, like the result with a p-value of this. Well, you're setting alpha, you wouldn't pick alpha anywhere and afterwards anyways. But if your alpha is higher than the p-value or the p-value is lower than alpha, you would reject the null. So this is another true fact. Yeah, you wouldn't pick it afterwards though. It's just if your alpha is higher than your p-value is lower than your alpha, you reject the null. Okay, here we go. 12, 22. I could chug like 4 Red Bulls. Don't tempt me. I'll do it. I'm drinking the whole Red Bull today. Going crazy. Who knows this? A, B, C, or D? Help me out. The name of the threshold by which we determine when we reject the null. The bar by which we choose to reject the null. So there's a trick to this because it is A. Oh, it's A. But it's also your type 1 error rate. I don't like that they did that. Type 1 error rate is described by alpha. That is literally the same thing. Great job, Emily, right there with 30 some more points. The alpha is the amount of time you make type 1 errors. So they're almost synonymous. We would say it's the alpha, but alpha dictates type 1 error rate. And the effect size is the true difference between the null and the truth. As in, like, if you believe that you can bench 500 pounds and you can only bench 499, it'd be hard to detect there's a difference. But if you can only bench 100 pounds and you think you can bench 500, that's a big effect because the truth is you bench 100, the null is you bench 500. You're going to find out pretty quickly that you're going to reject that null, you bench 500 pounds. Critical value are used for confidence intervals. We drew that out also today. And there it is right there showing the critical values. The critical values are going to be these, the Z's or the T's that dictate the percent confidence. And I don't think we still have this. Oh, we do. You find it right here, like 144 degrees of freedom, 95% confident, or you could do it on the normal curve if it's a Z critical value, and you go right here on the normal curve, and you say something like 98% confident, make sure to click between, and 2.3263. So you will get those critical values, which are used to make confidence intervals. So it's not confidence intervals, it's not type 1 error rate, false positives, it's not the effect size, the difference between the null and the truth, it is your alpha level. That's what it is. The next one right here, also pretty easy. What is it? What is the probability that a test correctly rejects the false null? Is it A, B, C, or D? I'll throw you some points again as I take the timestamp right here. The probability the test correctly rejects the false null. And throw some questions in the chat if you want. We should know what everything here is. Significance level is alpha. That's just another proxy for alpha, the point at which you reject. If your p-values are lower than this, you reject. Alpha, it's also your type 1 error rate. Type 2 error rate is known as beta. It is power. That is the right answer to this. Power is type 2 error rate is beta, and beta is when the null is false and we fail to reject it. That's a type 2. P-value is the probability of our results, or results from our stream happen by random chance variation given the null is true. And the power of a test is 1 minus beta. We do some textbook definitions on the test sometimes, where it might ask you what is power. And right here, as you see, can we? Yeah, sure. Katie, ask away. We'll do it right after the assignment here, but Katie, ask away about the project. Power is the ability to correctly reject the false null, as in the ability to find results if they exist. So a powerful test would find cheaters if they cheated. And the mathematics for power is 1 minus beta. So it's not making a type 2 error. And as you can see, the 3 things that increase power are type 1, alpha, more type 1 errors, more power, sample size, effect size, increased power, because they're inversely related to beta, which is type 2 error. So that is it. Yeah, ask away. We got it. 1 minus beta is power. Oh, these are too easy. A, B, C, or D as I take the timestamp, see if you know it. And really good work right here. This is too easy of a quiz. Or homework. We're going to be done with this in a moment. Be done with it. What is the name for the difference between the null and the true population parameter, the null and the truth? A, B, C, or D? Type 1 error rate is your alpha. It's your false positives. It's when you reject the null and the null is true. In a type 1 error, the null is true and we reject it. So it's not that. Critical values are used to make confidence intervals. So the critical values are the T or the Z, at least how we use it in this class. So here's the T's or the Z's. The critical values are right here. Notice I have them under critical values, and we've listed all the confidence intervals with all the components. The estimates, the critical value, and the standard errors are all listed below. And we were just going through some of the theory for them in class, talking about the 3 different intervals, chapter 15 and chapter 17, 15, 15, and 17. The bottom one is chapter 17. They all go by the same theory on that you have an estimate and then you have a margin of error. Drop a question in the chat, Katie. We'll be doing it here in a second. And the alpha level is the point at which you reject the null, is also your type 1 error rate, but it is effect size. Effect size is the true difference between the null and the truth. And that's what it is. Ooh, now we get to some tricky ones, the ones people came here for. Okay. How's everyone doing today? It is too nice of a day. I feel like I should get another coffee. Coffee, Red Bull coffee. A little crazy. A bank wants to know if the enrollment on their website is above 30%. So they're trying to do the alternative. If you're writing this out and they already did it for you, the alternative hypothesis would be the true enrollment on their site is above 30%. And they do a test right here and they do reject the null. So if they reject the null, the only error they could have possibly made is a type 1. We've actually narrowed it down to only these answers, not those. These two in the bottom one. The reason is because in a type 1 error, the null is true and you reject it. Memorize this. I'm going to go to the main screen for a second. Wrong button. We're going to hear some know your events. We're using median and IQR. How do you interpret? We'll do the interpretations of median and IQR next, Katie. You got it.
Know your variable types.
Know your variable types. So when you're doing these questions, memorize this. In a type 1 error, the null is true and we reject it. In a type 2 error, the null is false and we fail to reject it. There's 2 F's. In a type 1 error, the null is true, that's a T, and we reject it. In a type 2 error, the null is false and we fail to reject it. The 2 F's of the type 2. Let's go to the main screen. Okay. So later they find out that it's actually 28%. So they believe it's more than 30%. This is a huge type 1 error. So let's see. The way they phrase this gets me sometimes. The bank made a type 1 error. True. The actual value is not greater. That's true. I don't know what they mean by close to. This is mean. So we know that they rejected the null. We know they made a type 1 error. Well, it's not greater than. That's a fact. Don't be. I was about to be like, what does close to mean? What does close to mean? It's a fact that it's not greater than. The truth is that it's 28%, so they made an error. A student decides to test 100 students to determine whether they prefer soda brand A or soda brand B, and see if it's 50% or not 50%. Later, a marketing company comes in and finds no difference. And they find no evidence of a difference either. So think about this. The student finds no difference. And then the marketing company says, well, we tested everybody and found no difference. And since you tested everybody, you know the truth now. So the student did not make an error. Because they didn't reject the null. They said, well, it looks like there's no preference. And the marketing company tested everybody and found no preference. So they confirmed what the student found. There was no error made. A human resource analyst wants to know if the application this year's score on average higher than the placement exam that was 52 points for candidates last year. She samples 50 and she finds an average of 54.1. She fails to reject the null. Now think about the only error you could have made. In a type 2 error, the null is false and we failed to reject it. So she didn't find enough evidence. She didn't reject the null. At the end of the year, they find out the candidates had an average of 55.3, so they were higher. So she made a type 2 error. So she made a type 2 error. The actual value was 55.3, which is greater than. She should have rejected the null because she said, well, I didn't find enough evidence that it was really higher. It looks about the same. No, you should have rejected the null. You just didn't find a big enough result. A pharmaceutical company tests whether a drug relieves headaches from 25% achieved by the placebo. They failed to reject the null. So they didn't find any results, so it can only be a type 2 error. In a type 2 error, the null is false and they failed to reject it. It doesn't mean we made one. It just means they didn't find enough evidence. Further testing shows that the drug actually relieves headaches for 38% of people, so they should have rejected the null. So this is a type 2 error. Well, I think this has it right here. That looks right to me. The company made a type 2 error. The null hypothesis was not rejected, but it is false. The true relief rate was greater than. Hey, Catherine, good to see you there. Well, we got this. What's the last question right here? And then we're going to do Katie's question. What type of error is made when the true null is rejected? 1 or 2? You got a 50-50 shot. But remember your tricks on how to do this. What type of error is made when the true null hypothesis is rejected? If the null is true and you reject it, you've done what? Type 1. Nice and easy. Boom. Homework done. That's it. Quiz isn't that much harder. Great job, Katie and everyone. Let's do some, I've got that saved. I didn't even mark the question. It was so easy. Okay, let's do on the interpreting median or mean or IQR or standard deviation. So let's do 22. Stat 201 project interpreting. I can't spell. Mean, standard deviation, and if I come to in-person office hours tomorrow, yeah, of course. We'll be doing a lot of office hours tomorrow. I'll probably be starting at 11. I'll send some announcements about that since I changed it around today. It's been a crazy week. So thank you so much, everybody. More points in the chat. So many points from Ubot. Here we go, loading up some data. Okay. We'll go to the used car data set. Why would we use median? We can do Canvas content number 9 right after this. You got it. Let's do that. Why would we use mean or median? Ooh. Why would we use mean or median? You're welcome, Catherine. Why would we use mean or median? The shape. So which of these would you use median for, the top or the bottom? And Emily's basically saying it. So the answer, obviously, which of these would you use median for? One of these, they both have a little bit of skew, but the bottom one, you definitely should use median. The top one could be argued to be mean. There is a little bit of a skew, more pull to the left. And if you want to see if there's skew, you don't have to do this, but if you go to customize summary statistics and go to skewness, you can also ask for the IQR. It'll just tell you it. That was customized summary statistics, and there's the interquartile range. And if you click OK, you can see this is actually, it's more symmetric than I thought, even though the mean is lower than the median. But it has very little negative skew. This one has much more negative skew, left skew. And this one also has negative skew. This is the most skewed one. You can see it visually. So when you interpret this, remember we're talking about cars here. On the top graphic, I would say you could interpret the mean and standard deviation because it's normal. You should make that clear in your analysis. Like, this is how it looks. This is the shape. Because of this shape, the appropriate measure of center and spread, and do not use all of them. We only ask you give the appropriate measure of center and spread. So how would I interpret this? The average price of a car is, the average price of a used car is $21,204.85. The typical distance that a car is away from the mean is about 8,860.37, which is the median. Does that make sense? The standard deviation is a typical distance that something is away from the mean. That's what the standard deviation is. I think it's a standard deviation from the mean. So the typical distance that an observation is away from the mean is about 8,860.37. That's how to do the mean and standard deviation, and do that only for normal data. Don't use all of these. So how do you do median and IQR? Well, year. Okay. So here's how we would interpret the median for year. The 50th percentile for a year that a car was made is 2017.43, which represents 50% of cars are made after this date and 50% of cars are made before this date. It's the 50th percentile. Does that make sense, Katie, right there? The 50th percentile for year of car made. Oh my God, I just went to the mean. Ignore that number I just said. I was like, how can it be decimals? I mean, it could be a half because it could average 2018 and 2017. But the 50th percentile of year a car is made is 2018. There's the median right there. And that means 50% of cars are made at or after 2018 and 50% of cars are made at or before 2018. Does that make sense? That's the median. And then, thank you, Brandon, right there. I deserve that W after making that mistake. And then the IQR represents the range of the middle 50% of car year made, which goes from 2016 to 2019, which is a range of only 3. The IQR represents the middle 50% of car years being made, which spans from the 25th percentile at 2016 to the 75th percentile at 2019, representing an interquartile range of 3 years, which is the range of the middle 50% of car years made. So the IQR is the range of the middle 50% of whatever the data is that you're talking about. It's from the Q1 to Q3. Does that make sense, Katie? I'll drop some more questions. We're going to do Canvas content next. But that's got that. That's how to interpret those. Remember, don't interpret all of them. Only interpret the ones relative to your data and the proper shape. So it's Canvas content time. I think we're doing, is it confidence intervals and tests? We went out for our anniversary for dinner, and I couldn't eat an appetizer in my main meal. In a good way. Like, there was so many fries. I was actually shocked. We went to a Bistro by the Tracks, really nice place. Shouts to them. Really great food. You know, it's a fancier restaurant, but I felt it was worth the value. For nearly normal, if the sample size is 558, but it's very skewed, does that pass via the central limit theorem? It would. Make sure to quote the central limit theorem and talk about how the central limit theorem says that the distribution of the mean will get more normal and tighter for large enough sample sizes. That's a large enough n right there, which you have a sample way bigger than 100. So with the sample way bigger than 100, I would say you definitely pass. Talk about the central limit theorem, and hopefully Terry will tell the graders, make sure they know what the central limit theorem is. Canvas content, number 9. I'm trying to find it. There we go, number 9. 90s, we don't really. Good, it's good. I did it. Okay, Canvas content, number 9. Let's take a look. We'll do about 3 versions of this. A new diet is being tested. The inventor claims that you will lose 10 pounds on average. Researchers are worried about this claim and they think it's exaggerated. So what would the null hypothesis have in it? The null always has the what sign? The null always has the what sign? The null, we can narrow down this answer pretty quickly to 2, the equal sign. So now if someone believes the claims are exaggerated, they would say, I think the truth is you'll lose what to 10 pounds? Like, they're like, oh, you can lose 10 pounds in 2 weeks or 6 weeks. That's doable. I'd watch out. Usually they say about a pound a week. If the claims are exaggerated, they're trying to show evidence what? So this says, the null says the true mean weight loss is equal to 10 pounds in a week. What should the alternative be? That you'll lose more than 10 pounds or less than 10 pounds if we're trying to show it's exaggerated? If we're trying to show evidence it's exaggerated less than, there it is right there. A new diet is being tested, same idea, and now we get the data. This one right here, there's my results. Please do your TN voice. If you're watching this right now and you have a moment, Douglas, good to see you right there. Go check out the TN voice, whether you're in my class or another class, or you're just from another university and you can do the reviews of your instructors. Go do it. Help them out. Appreciate it. A new diet is being tested. The inventor claims you'll lose 10 pounds. That makes this value what in notation? I'm going to give you the rest of the notation. I want to see if you can figure out what that is in notation. A lot of people forget it. 25 people were randomly selected. That makes that the sample size. The sample yields an average of this much weight loss. That is Y bar then. The sample had a standard deviation of this. That is S. So what is that value up there? Does anyone know? That is the claimed weight loss. But what is it? I think it's just TN voice. People get stuck on this one, but it's just a notation thing. So this is running a t-test. So what is that value up here that I haven't filled out? Does anyone know what it is in notation? I want what mathematical notation is that? Who knows what the math notation is for that? If I write the equation for the t-test, I think you'll get it. It's going to be t with n minus 1 degrees of freedom equals the following. So what is that last bit of notation? It's mu naught. So mu naught is the claimed hypothesized value. It's mu naught. And so mu naught is literally equal, so you can say mu naught equals 10. So that's what goes over here on this side as mu naught. It's that the true weight loss is equal to some hypothesized value. So whatever this is the hypothesized value. And you can see that with like the null being p equals p naught if we're testing proportions. So whatever goes on the right is the hypothesized value that we believe is true unless we have evidence elsewise. So we can just run the math on this. This problem is really just solve the math for the t, I believe. So find the appropriate test statistic. It's asking us to calculate this right here. The appropriate test statistic is this. Now, this is not the t for a confidence interval. This is the difference standardized. The top of this equation is a difference. The bottom is the standard error, which standardizes it. So we go right here and do 10 minus 2.7. I reversed that. That'll make a positive t-score. We are actually going to get a negative t-score. So we want to make sure we do 2.7, which is the sample mean, minus the claimed value, which is going to be negative 7.7 or 7.3, negative 7.3 over, and then the standard deviation was 6.7 divided by square root of 25. So that's going to be 1.34, I think, 1.34. I'll write that down here. That's going to be a pretty large negative t, I believe. We're going to check our math, and we go 6.7 divided by 5, and there it is right there. We were right. And now we go back and we just solve the final bit of the top of the equation, 7.3 divided by that, and we get 5. It's going to be negative, though. Do not forget the negative sign. 5.45 negative. Negative 5.45. Does anyone know what the p-value would be on this test? Who knows what the p-value would be? Any guesses? Here, I'll draw it out for you. Ready? You're saying, but we need the applet. But wait, watch this. You landed all the way down here. If you land all the way down there, what is the area below here? If you land all the way down there at negative, then what's the area below there? We can go find it. Any guesses? You go down here, you go to a t with 24 degrees of freedom, you do below, and you drop in the negative version of this, and we find the p-value, and you go negative, and it's 0. There you go. You can get the decimal places, but there it is right there. And you notice it's off the curve. We'd have to like zoom in super close over here to see it. There's really nothing. So there we go. There it is. There's the p-value. This little tiny area which you can't even see over here. It's nothing. So the p-value is basically 0 because what we saw was virtually impossible given the claim is true. So it should be negative this, and it says enter into 2 decimals, and there we go. A smaller p-value provides stronger evidence against the null. Is that true or false? Or is it no answer text provided? A lower p-value provides stronger evidence against the null, to reject the null, or evidence for the alternative. That's not the trick of it. It's not really a trick. True or false? What do you think? A lower p-value is more evidence against the null. Well, the lower the p-value, the further you land away from the null. And the further you land away from the null, the less likely the null is true. So if you were to move this further over, what it would do is it would make the area smaller, and that means your friend ran slower. So you think about the running example right here, there'd be more evidence that your friend is not a 6-minute mile runner if they ran a 6:50. There'd be less evidence that your friend is a is not a 6-minute mile runner if they ran like 6:10. And at that point, this would be a much more likely result. So larger p-values don't supply evidence to reject the null. It's lower p-values because that means what you saw was less likely. This is a true statement. A type 2 error, is it A, B, C, or D? I want you to figure this out, and then you can do the next one for me. Help me out right here, and then I'll do another version. But a type 2 error, is it A, B, C, or D? You got this. If you're in my class and you've been memorizing this, this is so easy. This is a freebie. You get this on the test, you're like, yes, freebie question. Is it A, B, C, or D? In a type 2 error, there's the answer. In a type 2 error, the null is false. Oh, wait, Emily, 5,000 points. In a type 2 error, the null is false. But you got to remember the second part of it. In a type 2 error, the null is false. And so which one is it? I think you're about to figure it out. You're like, oh, wait a minute. It's just memorization. In a type 2 error, the null is false, and we fail to reject it. There's the 2 F's of the type 2. In a type 1 error, the null is true, and we reject it. When we reject the null and it's true, we made a type 1 error. There's no type 3, no type 4 as far as I know. Did we get it all correct? Did we do it, or did I make an error? Yeah, we did it. Let's do it again. Douglas, great job right there. This one right here, same sort of math as last time. The difference is 3.2. 3.2 divided by, I'm just subtracting those right there. We got the same standard deviation, it looks like. 3.2 divided by 1.34 is about negative 2.42. Let's see what we get. 3.2 divided by 1.34. Oh, it was really close. And check out the thing where we solved it just a little bit ago. I walked through the whole thing. Okay. This one we already did. We're trying to say they're exaggerated. It's going to be less than. A type 2 error is made when the null is false and we fail to reject it. When the null is true, we reject. That's the type 1 error. We construct a 95% confidence interval, and it does not contain the value. Does it? It doesn't contain the values. This is like the project right here. If your interval, and you say, I am 95% confident the true mean price of a steak is contained in the interval $30 to $40, and then the true mean price of a steak is tested where the mean is 50, what could you do to the value of 50 since it's not in the interval? Well, anything outside the interval can be rejected because intervals work this way. A 95% confidence interval shades the middle 95% of possibilities around what we find in the sample. When we do a test, if we do a does not equals test, then it works the same, but it shades the outside. So a 95% confidence interval is analogous to doing a two-tailed does not equals test with 5% alpha. And this is theory questions on the test sometimes. So the confidence interval at 95% is analogous to the does not equals two-tailed test. So we could reject this on a two-tailed test with 0.05 alpha. And so we could reject the value at the 0.05 alpha level on a two-tailed test because it wasn't contained in the interval. It does not contain it. I was double checking right there. I was like, does not contain it? Did I get the first one right? Got the first one right. We'll do another version right here. Please let me know if you have additional questions. We're just having some fun. If they believe it's exaggerated, great job, Brando, right there. It'd be B. Oh, you're that quick? Whoa. I'll throw 20,000 points if anyone can get this answer in 30 seconds. I'll put 30 seconds on the clock, see if you can get it. I'll give you points for just trying. $9.1. 1.3. That's easy. Easier. 3, 4, 5, 6. No way. No way. Is it really? Is it really what I think it is? Let me double check my math. I think it is. Wow.
Wow.
Does anyone know it? Give you 5,000 points for just trying. You want to solve all the math. It's a beautiful number. Check out the version when we started this where I did this slower. But this one I think is a very solvable version. Any guesses? I think it is -7. So I was like, no way, it's a whole number. A smaller p-value provides evidence against the null that is true. Further you land away, the smaller the p-value. When we reject the null and the null is true. Douglas! Let's throw Douglas some... Nice job. Yeah, if you just work all the math, you should get that. It just turned out so perfect. It turned out to -9.1 over 1.3 because it was equal to 0.9 minus 10, which is the top of the equation, and then it was 6.5. So that's why that turned out perfect over square root of 25. So then that's 6.5 over 5, and you start breaking that down, and you get 1.3. Yeah, so then it literally turns into that, and that's a 0. Someone's gonna be like, "Is that a 6?" No, it's a 0. So nice job, Douglas. Crazy points in the chat. So I think we got it. When we reject the null and the null is true, in a type 1 error, the null is true and we reject it. Type 1 error. Construct a 95% confidence interval does not contain the value. We can reject it with a 0.05 alpha on the two-tailed test. We can reject that at 0.5 alpha. And we did it. Yeah. Once you know how to solve these things, they're not that bad. I say that all the time, though. Like, it's not that bad. Like, Brian, I get it. It's not that bad. This is 2.5. 1.3 divided by 2.5. So pretty sure this is 2.93. Let me double check. I think it is. I think that's right. But negative. Whoops. A new dye is being tested. We think the claims are exaggerated. Oh, wrong. There we go. And we can reject the value at the 0.05 alpha level because it's not contained within the 95% confidence interval on a two-tailed test. When the null is true and we reject it, it's type 1 error rate. Low p-values. Oh, wait, we haven't done this one. True or false? Help me out right here. True or false? Low p-values are evidence of cause and effect, and Mubot gives hints for this. This is false. We don't talk like that around here. You don't say cause and effect. That's a freebie question on the test. Mubot gets mad about that. So did I get that one right that I did in my head? We don't prove things here. Yeah, exactly. Bad words. So I did get... Oh, no! Oh. Why did I do that? I mathed it wrong. 1.92? It's 2.6 divided by... I mathed it wrong in my head. I did so many. No, it's 2.5 divided by 1.3. There it is right there. I mathed it wrong. I added an extra 1 to it. I don't even know how I did that. Because what I did was I went 1.3 plus 1.3. And then I realized since the difference is 2.5, I was 0.1 higher. And that's where I mathed it wrong. Man, so close. Would have done the whole thing in my head. We'll do one more. I just had fun doing this. Here we go. Last one. Do I get one more? I do get one more of these. Difference is 1.6. This right here divided by 5 is 1.38, I believe. 1.38. So that's 1.6 divided by 1.38. Ay. So that's 0.22. So it's negative 1.1. Oh, the last decimal's going to get me. I'm just going to guess. Sure. There we go. I can show you the math here in a moment, but once again, we solved it. Write down your notation, solve it out, see if you can get it by figuring it out. And less than, because they're exaggerated, they're not cause and effect. If it's not contained, we can reject it at the 0.05 alpha level, so we can reject it. And a type 2 error is when the null is false and we fail to reject it. Did I get the first one right? Let's find out. And I got it. There it is. Ooh, look at that. We got it. It's because the standard error is s over square root of n. So you take 6.9 divided by 5, and that's 1.38, which I said. And then you take 1.6 and divide it by this, and that was the hard thing to do. I was like, oh, what is that going to be? I was like, what's it going to be? What's it going to be? There we go. Yeah, I like math. Who doesn't like math? Math is fun. Red Bull's fun. Everything's fun. Everything's awesome. So that's got it for now. What else do we need? What else do we got? Should we do a little chapter 16 quiz? We've done project. We've done a lot. WWs. I like it. And where's the quiz? Let me go get the quiz. Chapter 16 quiz. White label error. Oh, man. Got a few meetings today. Going to do another presentation. Shout outs to the group I'm going to be presenting to. I think it's the Information Science Club. I don't want to get the club name wrong. I'm excited. And document shared. Ooh. And then we even did a Mario Kart thing today. Shout outs to Jaden. I hope I did the project right. Nervous, but I looked over everything and I think I followed it. Nice job for the Boxplot part of the project write-up. How do you know if there's a relationship? Let's do that in the video. Let's do that. Let's put this in the video. It keeps wanting me to say what that is, and it's not that. Okay, 4513 stamp 201. So we're gonna go here in project Boxplot interpretations. So knowing if there's a relationship is very subjective, because to what degree is there a relationship is kind of what you want to be thinking about. Let's go here and do the graph builder, and we're going to throw in here price, and let's just go here by model. Oof. Brand, there's only Ford cars. Color, oof. State, oof. Big oof. Really? Title status. Yes. Okay. Hey, does anyone want to buy my salvaged car title? This is about as big of a relationship as I've ever seen right here. Does anyone want to buy my salvaged car title? Look at this. You're going to go down here and do 5 number. Your graphics should look like this when you hit done. And here we go. Is there a relationship between your car's price and whether the title is salvaged or not? Is there a relationship? This one is a clear one. Is there a relationship? You're welcome, Emily. Have a great day. I would say, yeah, there's a relationship between whether it's a salvaged title or not when you buy a used car. We see clearly, looking at the 50th percentiles, that the salvage car titles have a 50th percentile of 3,500 versus the non-salvage title of 23,000, which is almost 20,000 more, or like 5 times bigger. You could do the math on it and be like, it's 5 times more, it's 20 times bigger. It's just big differences right here. Even the maximum shows huge differences between a salvage title and a clean car, where the salvage car only has a maximum car value of $13,500 and the clean cars without the salvage title have a $46,000 value. Also, there's a greater range. Even the range of the values via the IQRs are about similar, but let's go to the ranges from the max to the min. Range on the clean cars from $1,700 to $46,000 versus the salvage cars range from $250 to $13,500. I know, Colin. Good to see. Shout out to Colin right there. So proud of you, man. Hope you're doing well. And I did a big presentation day for the AI group. Going to present to a student group tonight. Drinking my Red Bulls. We're shouting out Colin right there. And part of the Haslam Young Alumni. So, and if you in the future want to be part of Haslam Young Alumni, I'd love that, because I wish all my students came back and said hey to me. It's like, I wish every student swung back by and was like, hey, Brian, I had you 2 years ago. I'm so glad you had a great time. It was good seeing you. I'm glad you tell me when you're in town. I'm serious. Let me know every time. Like, I'll swing by campus. I come here all the time. I like it. I want to see my students. And that way, when I'm like 90 years old and I'm walking around campus and people are like, that's old man Brian. He's been here for 60 years. I'm like, hey, students. I actually started when I was 30, so it'd be true. I'd be here for 60 years. I'll do it. I'll still be teaching at 90. It's my goal. # life goals. Teach at 90. I mean, who wouldn't want to just like hang out on a college campus and teach their whole life? It's fun. Something enjoyable. You get to sit in a nice chair, teach. So with this right here, there's a huge relationship. Exactly. That's the thing, Katie, right there. So you want to look at how big the differences are, whether you see big differences or small differences. And this is about as big of a relationship as it can be. You know, if you're seeing, as Colin points out right there, the asset depreciation, depending on the title, it's like, yeah, you got a salvage title. Someone's like about to sell my car. And you're like, ooh, it's got a salvage title. Ooh. Because, it doesn't mean you're going to not sell it for as much than someone else's car, but typically speaking, the typical salvage car has a median of about $3,500 versus the typical non-salvage car, which I don't know what cars are being sold here, typically for $23,000, but the median right here. And we would compare medians because there might be some light skew to this data. But yeah, if you go for values that are not as skewed, like let's go for mileage and see if they look different. We'll see if we get something. Title is really the only. This one is due to a lot less of the data. Someone's buzzing. That's a huge relationship too. Who's buzzing me? It's my mom. I don't know. She'll be like, "You're on YouTube." Yes, mom. She'll be like, "Brian, I need your mom. Stop. I'm on YouTube." I called her earlier today, see how she was doing when I was driving back from the event. But she didn't answer. No, I'm not answering. So right here, you can see a big difference too. Let me find one where there's not a difference. It's subjective on when there's a difference. It just, if you think there's a difference. Yeah. Okay, let's see. I'm going to narrow this down really quick. We're only going to look at water and normal Pokemon. Watch there be a big difference. See, that's the cool thing about Jump. You can just narrow down data that quickly. And now we only have water and normal Pokemon. I just want to do a side-by-side of two. And we go down here, type, put it over in color, and let's look at the hit points. Let's see if we can find something more. Attack. Oh, yeah, look at that. Yeah, this is where they're mostly similar. They're not perfectly similar, but this is where they're mostly similar. At this point, I would say there's... Hey, Ruton, good to see you there. Good to see you. We're going to have some big off-stars tomorrow because we got the big project and everything, but swing by. So if you look right here, these look mostly similar. Like the medians are very close. What we do see is small differences in the range of data where normal Pokemon have a bigger range going from the min to the max. A range of 155, you can subtract those values and see there. Where there's a slightly smaller range on the water Pokemon. The normal Pokemon also has more outliers versus the water. They are kind of similar in there's 2 low outliers and 3 high outliers versus just the 1 high outlier there. We are back in person tomorrow, you're right. And you can see the differences in the medians where the median normal Pokemon has a value of 70.5 attack versus the median water Pokemon has a value of 72 attack. The IQRs are slightly bigger. You can just tell visually. The IQR here is 39. Just subtract those numbers. Double check. I did divide. I don't want to divide. 92 minus 53. There we go. And the IQR over here is 31.3. You can just subtract 86.3 minus 55. And there you go. So it's slightly bigger range on the normal due to low/high outliers. The 5 of them total, 1, 2, 3, 4, 5. And slightly bigger IQR over here, suggesting a bigger range of the middle 50%, going from 53 to 92. Overall, these are slightly similar with just some small differences in the medians and some range differences and quote the values. Does this make sense here, Katie? These are more similar than the other one we made earlier. I might not still have those up, but oh, there we go. Yeah, this is some pretty crazy big differences. Like these are good examples. Yeah, if you have more questions, drop them. This one on the right is pretty distinct differences. That's where there's a clear, strong relationship between the mileage on a car. I mean, look at that. Like, I mean, you're an outlier if your car has like 100,000 miles and it's a clean title. I mean, I know my wife's car had like 200,000 on it, but yeah, clean title, I think too. It's so, yeah, but, and this is, I don't understand where this data set comes from. I got to look at the used car data set. But the cars up here, the salvage titles have on average like 100,000. Like that's typical. The 50th percentile is right at 100,000. Where down here, the 50th percentile is 30,000. Yeah. We've done some really great work today. Probably do more of the assignments tomorrow. Oh man, so many things. I'm wearing new contacts. I can't tell if I love them or hate them. I can't tell. Can't tell. Well, I might take a break. And I can't believe this week is half over. We got a lot of big things to come. There's going to be big events, big times, and we got the project. But I'll give everyone some 5,000 points. Going to go on a quick walk, then some more meetings. But huge thank you to everybody. I think we have all the things saved. And we did the homework. We did some project. Let me write right here. Project and Canvas content. Canvas content. You're welcome, Jaden. Hopefully everyone got I think everyone should have the homework done. We did the full thing. We've been working on the project. But any last questions before I go? Let's see if I have any Red Bull. You're welcome, Brando, and I really appreciate it. It's like, people are working really hard. I gotta say that. Like, I know it's a lot to like swing by and like, you know, you got life and everything. And I love it when people swing by live because like, I don't know. Like, I know maybe sometimes I work quicker when I'm just here by myself and there's no one for me to ask questions to. But someone said to me, how do you do it? They said, how do you like interact with people online? And I'm like, they talk to me and they're like, they talk to you. They're like, I have my student, because really quick on this, people say to me, I'll go to the main screen. People have told me they feel better talking in this chat than they do in classes that where you have to be on your webcam. Like if you're in a class and you have to be on your webcam, people hate that. They tell me, they're like, I hate being on my webcam. I hate just sitting there and like everyone's staring at each other. You're just like, sitting there staring at each other. But then people told me about this class. They're like, I can just sit here and just like, some people put it on like a big TV and then they'll have their phone and they'll just be like just typing me on their phone. And then they'll see it on the TV appear and everything. And they're like, oh, Brian's talking to me. Hey, what up, Brian? And then I'll be on the TV. So it's kind of neat seeing what people have done. They put me on like bigger screens and they're like, oh, dude. So I got to say, I'm really lucky that here in Haslam, they're like, yeah, dude, do your class on YouTube. It feels forced when you're on a webcam and you have to sit there and be like, everyone hates that. Everyone hates that, like, just staring there blankly and just, like, got to keep your webcam on. There's so many people who do, like, the thing where they, like, record themselves and they just, like, loop it. And then the teacher's like, raise your hand if you think this, or click something in the chat. It's tough. It's tough for us educators because we have to create interaction. We don't have to. But if you don't make your class interactive, everyone falls asleep. No one listens. Like, I could teach every single class I do in easily half the time if I just told you everything. But then no one would learn it. It wouldn't stick. So I have to come up with examples. I like that. But I could just burn through classes. And there was this one time I wasn't feeling well and I just like burned through the material. I call it burning through because you're not helping the students learn really. But I was not feeling well and I was like, and I just like started just go through the slides. I was like, yeah, p-value is this is this is so bad. But I was not feeling well, and I was like, I have to get through this. But probably didn't help my students learn. It's a bummer. So then I usually try to do things. I try to make up for it and try to help out. But we all have our off days, right? Well, with that, huge thank you to everybody. I'm going to go on a quick walk. Then I've got a few meetings. But we'll be back here tomorrow. We're going to do some big office hours. So swing by those in-person office hours. Send me some emails. I'll be replying to emails because I'm hanging out on campus for a bit. Till then, bye for now, everyone. Bye. It's my tagline.